Hello and welcome. In the previous video, we talked about how we use a correlation coefficient to measure the strength of a linear relationship between two variables. So that's useful, but we might want to go farther than that and talk about more than just the strength of that relationship. We might also want to know about the slope of that relationship and be able to use values of one variable to predict values of another. So what this boils down to when we're talking about linear relationships is how we best draw a line through our data points to represent the relationship between the variables that we're looking at. So in this lecture, we're going to start talking about this regression framework for understanding data. We're going to be covering a lot of ground in this video because regression is a big topic in data analysis. So let's get started by looking at the data that we were talking about in the previous video. So this is again data on the percentage of people living below the poverty line and the percentage of high school graduates in each of the 50 states plus Washington, D.C. So each of the data points in this scatter plot is a state or D.C. And we want to be able to draw a line representing the linear relationship between these variables. So in this scatter plot here, we have a couple of different possible lines, A, B, C, and D. So take a minute and look at those and see which line you think best represents the relationship that we're looking at. So it should be pretty clear that lines B and C are not capturing the relationship between these variables very well. They don't tend to follow the trend of the data points that we're looking at here, but it's a little bit more difficult to tell whether line A or line D is better capturing this relationship. Now, it turns out that line A is the best line through this data by some criteria that we're going to talk about in just a minute. But how do we know what line is the best? What are the criteria that we have for deciding what a best line through these data points looks like? A really key consideration as we're drawing a straight line through our data points is something called residuals. Now, residuals are the leftovers from the model fit. So when we draw a straight line through the data points are not all going to lie directly on that line unless we have a situation of perfect correlation, which usually we don't. So there are always going to be some distances between the actual data points and the line that we draw through those data points. So we have all of these vertical distances of the actual observed data and then the distance to the line that we've drawn through the data. These distances are always vertical because we're talking about the variable that's on the y-axis. So that vertical axis is representing the outcome variable that we're interested in. And so we look at the vertical distances of the data points to the regression line. So let's talk a little bit more about these residuals. So for each observation, which we're going to denote with the letter I, the residual is the difference between the observed value of the dependent variable and the predicted value of the dependent variable. Now, when we have a predicted value, we denote that with this little hat symbol above the variable. So the predicted value is y hat I, so that's the predicted value for observation I. And the actual observed value is just yi. So there is a residual associated with each of the data points that we have in this scatter plot. So let's talk about two of those in particular to illuminate this a little bit more. So there is a green dot above the regression line in the scatter plot, and that green dot is representing our data on Washington, D.C. So we can see that we observe a poverty rate of a little more than 17% in Washington, D.C. But when we follow that straight down to the regression line, the associated predicted value for Washington, D.C. is only about 12%. So the percentage of people living in poverty in D.C. is 5.44% more than we predicted. So the residual for Washington, D.C. is 5.44. Similarly, there is a point below the regression line that is our data for Rhode Island. So the percentage of people living in poverty in Rhode Island looks like a little bit more than 10%, but the predicted value, when we follow from that data point up to the regression line, the predicted value is closer to a little bit more than 14%. So the difference in that poverty rate is about 4.16. So the poverty rate in Rhode Island is 4.16% less than we predicted. So that residual is negative 4.16. As we try to find the best line through our data points, our key rule of thumb is going to be to find a line that has small residuals. So this is a line that gets really close as possible, to as many of the data points as possible, basically. And there are two main ways of thinking about minimizing residuals. The first is to minimize the sum of the absolute values of residuals. So this just takes the difference between every data point and the regression line, takes the absolute value of that distance, and sums all of those distances up for all of the data points in our sample. The second way of thinking about minimizing residuals is to minimize the sum of squared residuals. So this takes the distance between each data point and the regression line and squares it, and then adds up all of those squared distances to get the measure of the total residuals around that regression line. So this is the least squares option. So we're trying to minimize, find the least sum of the squared differences from the data points to the regression line. And it turns out that actually minimizing the sum of squared residuals is the most commonly used method for this minimizing residuals condition that we want to satisfy when we're trying to find this best line. And there are two main reasons for this. One of them is practical. It turns out that when we're doing a minimization problem, it is a lot easier to minimize a quadratic function, so a function of squares. And that's easier when you're computing by hand, and it's easier for a computer to minimize as well. So that's a practical reason. And then it also has the effect of really penalizing big misses. So if the regression line is really far away from particular observations, that line is going to get penalized more. The sum of residuals is going to be greater when we use the squared residuals method. So imagine that you're taking the sum of the residuals, and you have a data point that is 4 units away from the regression line. If you do the absolute values method, you're going to add 4 to your sum of residuals. If you use the squared residuals method, you're going to take 4 squared, or 16, that gets added to the sum of residuals. So it's just a different way of thinking about how to deal with points that are really far away from the regression line. Putting those mathematical and computational details aside, here is the formula for finding points along the least squares line. So we have y hat is equal to beta naught plus beta 1 times x. So let's go through what each of those variables means. Y hat is the predicted value of the dependent variable. So our dependent variable, our outcome variable, is denoted with the letter y, and we put a hat over it to indicate that it is an estimate for the value of the dependent variable. Beta naught, so beta sub 0, is equal to the intercept of the least squares line. Beta 1 is equal to the slope of the least squares line. And x is the value of the independent variable, the explanatory variable, in our equation. So we're going to go through the intercept and the slope in a little bit more detail in just a second. But let's talk about notation just really quickly. So we have made sure to distinguish throughout this class between our sample statistics, our sample estimates, and the actual parameter in the population. So the parameters we're going to denote with this Greek letter beta, and the point estimates that are drawn from our sample we're just going to denote with this lowercase letter b. So for the intercept, our parameter is beta naught, but our point estimate is b naught. And for the slope, our parameter for the population is beta 1. Our point estimate from the sample is going to be denoted as B1. Let's return to our example to talk a bit more about how we find and interpret the regression line. So remember, we're looking at the relationship between the high school graduate rate and the percentage of people living in poverty in each of the 50 states plus Washington, D.C. So here is some summary data about those variables. So the mean high school graduation rate is 86.01%. That has a standard deviation of 3.73. The mean percentage in poverty is 11.35%, and that has a standard deviation of 3.1. And like we learned in the previous video, these variables are correlated with one another, and that correlation coefficient, R, is equal to negative 0.75. So using that information, let's go ahead and see how we find the regression line. So finding the slope of the regression line is actually really straightforward. So we use our computational software to find the correlation between the two variables. That's denoted again by this letter R. And then all we need to do is multiply the correlation coefficient by this fraction, the standard deviation of y divided by the standard deviation of x. So that's the standard deviation of our dependent variable divided by the standard deviation of our independent variable. And again, this is just for this bivariate regression where we have one independent variable and we're looking at the effect of that independent variable on our one dependent variable. So in our example, based on the data that we talked about on the previous slide, this is going to solve out to 3.1 over 3.73, so the standard deviation of y over the standard deviation of x, times the correlation coefficient, which was negative 0.75, which is equal to negative 0.62. Now, a useful thing to know is that because standard deviations are always positive, this standard deviation fraction here is always going to be positive, which means that the slope of the regression line is always going to have the same sign as the correlation coefficient. So if the variables are negatively correlated with one another, then the slope of the regression line will be negative. If the variables are positively correlated with one another, then the slope of the regression line will be positive. So that's good to know. We're going to interpret the slope by saying that for each additional percentage point increase in the high school graduation rate, we expect the percentage of people living in poverty to be lower, on average, by 0.62%. So more generally, the slope tells us how the dependent variable responds to a 1 unit increase in the independent variable. So when the independent variable increases by 1 unit, in this case the units of the independent variable are percentage points, but when the independent variable increases by 1 unit, what happens to the predicted value of the dependent variable? In our particular example, because we found this slope of negative 0.62, we say that a 1% increase in the high school graduation rate is associated with a 0.62% decrease in the poverty rate. The other parameter for this bivariate regression line is the intercept. So the intercept that we're going to calculate from our sample is B0. So this is the point where the regression line intersects the y-axis, so where the regression line crosses over the vertical axis. So an interesting fact about the regression line is that it always passes through this point at the mean of x and the mean of y. So if on the x-axis you find the mean of x and you follow that up, and on the y-axis you find the mean of y and you follow that across, where those two meet, that point at the mean of x and mean of y, the regression line is always going to go through there. So using that fact, we can calculate the intercept by saying that the intercept is equal to the mean of y minus the slope coefficient times the mean of x. So what this means is that you can, if you have the slope coefficient and the mean of each of your variables, you can easily calculate the intercept. So if the mean of x is 0, then the regression line crosses the y-axis right at the mean of y. And so that's how we use this information, that the regression line always passes through this mean of x, mean of y point. to find this sort of more general formula for the intercept. The intercept is important for telling us where the regression line is going to go. So imagine that we had a line with the same slope, but our intercept was lower. So imagine like shifting this line with its same slope down a bit so that it intercepted at a lower point on the y-axis. If the intercept was lower, this line would miss our cloud of data points entirely. So where the intercept is really important. So using this formula of y bar, the mean of y, minus the slope times the mean of x, we can calculate where the intercept would be for this example that we've been working through. So in our data table a couple slides ago, we had the mean of each of those variables, and we just on the previous slide calculated the slope coefficient. So we have all the information that we need. We're going to take the mean of y, 11.35, minus the slope coefficient, negative 0.62, times the mean of x, 86.01, and we find an intercept of 64.68, which you can see in this graph above. That's where the regression line crosses the y-axis. So we should understand why knowing the intercept is important, how it tells us where our line is supposed to be located in this two-dimensional space that we're working with. But what does it tell us in practice? How are we supposed to interpret the intercept? I've given you a couple of options here. One of them is the correct interpretation of the intercept. So pause the video, take a minute and read through these, and see what you think is the correct answer. The intercept is where the regression line crosses the y-axis, which means that the regression line is the predicted value of y when x is equal to 0. So what this means is that when, in our example, x, the high school graduation rate, is 0, the predicted value of y, the poverty level, is 64.68%. Now, of course, in reality, we don't have any states where the high school graduation rate is 0, where there are no high school graduates who live in the state. That would be pretty ridiculous. And so finding a predicted value of the dependent variable under those circumstances is not really very useful, and it's certainly not reliable. Because we don't have any data for states with that kind of characteristic, with no high school graduates, it doesn't make sense to really try to estimate the poverty rate in a state like that. So the intercept is more useful for just telling us the placement of this regression line, and it's the portion of the line that actually goes through the data points that we observe that's going to be more informative about giving us a predicted value for the poverty rate, conditional on the high school graduation rate. But the actual interpretation of the intercept is the predicted value of y when x is equal to 0. So you just need to pay attention to your data and understand whether the intercept has a practical and meaningful interpretation, or whether the value of x being 0 is something that would never occur in the real world. So let's sum up what we've learned here. So here again is our data on poverty levels and high school graduation rates, and here is the least squares regression line that we fit through those data points. And this up top is the equation that we have to get that line. Our y value, our y hat, the percentage in poverty, is equal to 64.68, the intercept, minus the slope coefficient, 0.62, times our value for the high school graduation rate. So we could use this formula to predict values of y for given values of x. So if I said, okay, so what is my best guess for the percentage of people in the state who live in poverty if the high school graduation rate is 90%? So I would input 90 for the percent of high school graduates, and then I would solve for the predicted value of y. And that is how the regression line works. So let's just recap one more time how we interpret the parameters of the regression line. So the intercept is where the regression line crosses the y-axis. So this is the predicted value of y when x, the independent variable, is equal to 0. And then the slope of the regression line tells us how much y changes depending on each unit increase in x. So when x increases by 1 unit, how much does our predicted value of the dependent variable increase or decrease? So keep in mind that these are not causal statements. This doesn't tell us anything causal or deterministic about the relationship between these two variables. First of all, there is plenty of uncertainty around this regression line. So remember when we were looking at our example, we have points all over surrounding this regression line. This is just our best approximation through those points. And doing a regression doesn't tell us anything about the direction of the causal relationship. So this doesn't tell us that x causes y. This just gives us our best fitting least squares line through the data that we have in our sample. If we do a randomized controlled experiment where we randomly assign values of the independent variables to our subjects, then we can do causal inference, and we've satisfied those conditions. But that is a separate question from how we draw the regression line. So just drawing the regression line, performing this calculation in and of itself doesn't tell us anything about the causal relationship between these variables. We talked about this briefly already, but we can use our equation for the linear model to generate predicted values of our dependent variable when we have particular values of our independent variable. So this is just a prediction. We take the value of the independent variable that we're interested in, we plug it into the equation, and we solve for the predicted value of y. Now, of course, keep in mind that this isn't going to give us the real-world value of y. There's always some uncertainty associated with the predicted value, but it does give us our best guess based on the linear model equation that we found. If, when we do this, we plug in a value of the independent variable that doesn't occur in our data, that's much higher or much lower than the data that we have in our data set, then what we're doing is called extrapolation. So we are plugging in a value for x that we don't actually observe. And it might be the case that that value of x makes sense in the real world, and so it's okay to go ahead and see what our predicted value of y is, or sometimes the value of x that we would plug into our equation doesn't make much sense. So when we were finding the intercept, we talked about the fact that setting x equal to 0, the high school graduation rate equal to 0, doesn't make sense as a real-world condition. Now, of course, we need to do that to find the intercept, and there's no problem with that, but we can run into problems if we try to use our regression model to make predictions based on values of x that just aren't sensible. So one of the things that we've emphasized throughout this class is that there are always conditions for inference. So there are always some things that we need to be true in order to make sure that the inferences that we draw from our data are valid. So we're going to talk about these main conditions for when we're doing a least squares regression. Those conditions are linearity, nearly normal residuals, and constant variability. So let's go through each of these in turn. The first of these conditions is linearity. So all this means is that the actual relationship between the explanatory variable, the independent variable, and the response variable or dependent variable should be linear. So linear regressions are able to capture linear relationships. If there is a nonlinear relationship between the variables that we're interested in, then a linear regression is not going to do a very good job of capturing the actual relationship between the variables. In the previous lecture, when we were talking about correlation, we talked about a couple of examples of the sorts of relationships that a correlation coefficient is not able to pick up on. Correlation coefficient is based on finding a linear relationship between variables, and a linear regression works in the same way. So there are methods out there for fitting models for nonlinear relationships. So if the shape of the relationship looks more like a parabola, or if there are curves in the relationship, things like that. There are methods out there for fitting those models. For the most part, we're not going to talk about those much in this class. I am going to upload an extra, like a couple of pages in a PDF from the people who did your open interest statistics textbook. That talks a little bit about a couple of those methods for looking at nonlinear relationships. But just keep in mind that when you're using the linear regression methodology, there needs to be an actual linear relationship between the variables that you are studying. When you're doing a bivariate regression, when you have just one explanatory variable for your one response variable, you can look and see if this condition is satisfied by just looking at a scatter plot of the data. So if the relationship between those data points looks more or less linear, if you're not seeing any big curvatures or anything like that in the data, then you can be pretty satisfied that this relationship is linear, that this condition is satisfied. Another way that you can check this condition is to generate what's called a residuals plot. So what this does is it just plots all of the residuals after you fit your regression line. So we talked about how we find residuals, and then we would just visualize those residuals. So in the plots below, the bigger square plots are just a scatter plot of the data, and then below is the associated residuals plot around each of those regression lines. So you can see on the far left, the bivariate scatter plot just of the data. Looks like that data is more or less linear and scattered pretty evenly around that regression line. And you can see that in the residuals plot, that data is still pretty much scattered pretty evenly around the mean of 0 in the residuals. In the middle plot, when you plot the bivariate relationship, just looking at the data, you can see that there's some curvature around that regression line. And also, when we plot the residuals, we can see that for some parts of the data, our residuals are consistently negative. Then in the middle of the data, the residuals are consistently positive, and then they drop off and they're consistently negative again. This is a sign of nonlinearity. So if you see something like that when you plot the residuals after doing a regression, that is a sign that this condition is not satisfied. So let's talk about what a residuals plot looks like in just a little bit more detail. So we were comparing the predicted values and the observed values for the poverty rate in Rhode Island and in Washington, D.C. a little bit earlier in this lecture. So let's just reiterate really quickly how we got to those predicted values. So for Rhode Island, we take this linear regression formula that we have, that y hat is equal to the intercept plus the slope coefficient times our value of the independent variable. And that's going to be equal to, we found an intercept of 64.68 plus our slope, which is negative 0.62, times 81, which is, there was an 81% high school graduation rate in Rhode Island, and we found a predicted value, a y hat of 14.46 for Rhode Island. But we actually observe a poverty rate of 10.4% in Rhode Island in this year in our data. So that gives us a residual, a leftover of negative 4.16. So when we do a residual plot, see this residual plot is the lower plot here, and we can find Rhode Island as this green triangle. And that residual is 4.16 below this mean of 0, right? So we have this dotted line equal to 0, and we can locate the green triangle representing Rhode Island about 4 units below that, indicating where Rhode Island's residual is. And that's how all of these different residuals are plotted out in a residuals plot. So when we have just a bivariate regression, the residuals plot sort of looks like the plot of the data just tilted on its side so that the regression line becomes horizontal. Things get a little bit more complicated when we're dealing with multiple independent variables in a regression, which we're going to be talking about in lectures in the future. So I just want to talk a little bit about how residuals plot looks and how you would find an individual observation in a residuals plot. And where its location on that plot is tells you about what the magnitude of the residual is, as well as the direction of the residual. And really briefly, we could do the same thing for Washington, D.C. So Washington, D.C. is the red square in these plots. And so we found a predicted value for y hat of 11.36%, but we observe a poverty rate of 16.8%. So that gives us a residual of positive 5.44%. So you can see in the residuals plot at the bottom here, the Washington observation, this red square, is 5.44 above this dotted line of 0, indicating that Washington's residual is positive 5.44. The next condition that we need to check is whether our residuals are nearly normal. So whether when we plot out our residuals, they're nearly normally distributed around this mean of 0. So that essentially means that we're looking for there to be lots of small misses, so lots of observations that are pretty close to the regression line, either a little bit higher or a little bit lower, and that big misses are rarer and rarer the bigger and bigger they are, just like a normal distribution. So this condition might not be satisfied if we have really unusual observations that are just really dissimilar from the rest of our data, so big outliers and things like that. So we can check this condition by plotting our residuals. So the way that we do this is we estimate a regression, we save our residuals, and then we plot them. We can look at the histogram, and then we can look at this normal plot, this QQ plot of the residuals, and see if it looks nearly normal. So we're going to talk a little bit more about how to do this in the lab for this week, but this is what that condition looks like and how you would verify it. The next condition that we need to pay attention to is constant variability. So this condition sort of comes in two parts. First of all, it means that the variability of our data around the least squares regression line should be roughly constant. So that means that how these data points are dispersed around this line should be relatively the same at all points along the line. So we don't want it to be the case that we have in part of our data set that our points are really closely clustered around the regression line, and then they start to get farther and farther and have a bigger and bigger variation away from that line as the data goes on. So if we run into that problem, that's something called heteroscedasticity. And what this also means is that the variability of residuals around this mean of 0 should also be roughly constant. Those two things go together. So again, that means that there should, when we plot our residuals, our sort of big misses and small misses should be sort of evenly dispersed at all points along this line. So we shouldn't have like all small misses at first and then lots of big misses later, or all of our big misses at first and then lots and lots of small misses. We want those things to be sort of randomly dispersed around. So that condition is constant variability. It's also known as homoscedasticity. Again, we're going to talk about how we verify this a little bit more in our lab, but again, we're just going to look at a histogram or a normal probability plot of the residuals from our regression to verify that. So lots of times it's pretty easy to tell whether these conditions are violated just by looking at plots of the data and of the residuals after we estimate a regression. So take a look at these plots, this plot of the data as well as the normal residuals plot from this linear regression, and see if you can tell which condition the model is violating. Okay, so pretty clearly these variables have a parabolic relationship between them, so they're not clearly linearly related to one another. That relationship is nonlinear, so estimating a linear model to try to characterize the relationship of these variables is not going to be the most useful thing. So that's the condition that this model is violating. And let's try one more example of this. Take a look at this plot of the data and of the residuals after estimating the regression, and see if you can figure out what condition the model is violating. The answer here is that those data points are getting more and more dispersed, more and more variable around the line as the data progresses. So the condition of constant variability is not being met here. So the variability of that data around the line, both around the regression line and around this mean of 0 in the residuals plot, is being violated. So this is a problem of heteroscedasticity, so differences in variance. So let's say that we want to know overall how well our linear model is doing at capturing this relationship between the variables that we're interested in. So we have a statistic called R squared that is going to tell us the strength of the fit of a linear model. So we're not going to go into specifically how R squared is calculated, but I am going to tell you what it means. So R squared tells us what percent of variability in the response variable y is explained by the model. So R squared is something that R is going to return to you when you estimate a model in R. It is something that ranges between 0 and 1. So if you have an r squared of 0, that means that the independent variables in your model are not giving you any useful information about predicting the value of the dependent variable. If you have an r squared of 1, that would mean that your independent variables are perfectly predicting your dependent variables. Usually you won't have an r squared anywhere near that extreme. You'll have an r squared somewhere between 0 and 1, meaning that somewhere between 0% and 100% of the variability in y is explained by your model. The rest of the variability in y is going to be explained either by variables that you didn't include in your model or by just inherent randomness in your data. So there's just random error in the world, things that affect the value of the response variable that you're just not going to be able to collect data on or model. So for the example that we've been talking about, r squared is equal to 0.38. Based on the information I just gave you, what is the correct interpretation of this r squared value? So the answer is that 38% of the variability in our dependent variable, remember our dependent variable is the percentage of people living below the poverty line, 38% of that variability in y is explained by this linear model, where the independent variable in the linear model is the high school graduation rate. So recall that our two primary types of data are numerical and categorical data. And so far in this lecture, we've been talking about doing a linear regression where both our dependent and our independent variables are numerical. So what happens if we want to model categorical data? Well, to do a linear regression, we do need our dependent variable to be numerical, but we can use categorical data as an independent variable when we're doing a linear regression under one particular condition, which is that we have to turn that categorical data into a dichotomous variable or a dummy variable. So let's talk about how we do this. So let's say that we want to know if the poverty rate in states is related to what region that state is in. So region is a categorical variable. It's not numerical. There's no way of putting regions on a number line. They're in different categories. So first thing that we're going to do is we're going to dichotomize the region variable. So we're going to decide whether a state is in the west of the country or the east of the country, for example. Now remember that a dichotomous variable or a dummy variable takes on values of 0 and 1. So let's say that in this variable that we're creating, if a state is in the west, it's going to get a 1, and if a state is in the east, it's going to get a 0. And we're going to create this single variable called west, which is going to indicate with a 1 every state that is classified as being in the west. And that is the variable that we're going to put into our model. So that means that we are indicating all of the western states, and the reference level is eastern states. So what we don't do, we don't put an indicator variable for west and an indicator variable for east, both in the regression. That causes estimation problems for some complicated reasons I'm not going to talk about. So we have to have a reference category left out. So we have our indicator variable for west left in the model, and the states in the east are left out as a reference level. So this is going to give us information about both western and eastern states, but we only put the west variable in the model. So west is our explanatory variable. And we're going to go ahead and estimate this model, and we find a linear model with an intercept of 11.17 and a slope of 0.38. So B1 is equal to 0.38. So let's talk about what that means. So remember that the intercept, B0, tells us what the predicted value of y is when x is equal to 0. So when x is equal to 0, that means that the state is in the east in this variable that we've coded this way. So when x is equal to 0, the predicted poverty percentage is 11.17. It's equal to the intercept. So this is a case where the value of the intercept matters quite a lot. So that's how we tell our predicted poverty level for states in the east. And then the slope of the the regression line, so B1, 0.38, tells us the estimated change in the outcome variable for a 1 unit increase in x. So a 1 unit increase in x, this region variable, means moving from value 0 to value 1, or moving from an eastern state to a western state. So this tells us that the estimated average poverty percentage in western states is 0.38% higher than in eastern states. So the estimated average poverty percentage in eastern states is equal to the intercept when x is equal to 0, and the estimated average poverty percentage in western states is equal to the intercept plus 0.38 times x equal to 1, right? So that's 11.17 plus 0.38, which equals 11.55%. So when we include a categorical dummy variable in our model, this is going to let us generate predicted values for y at both levels of that variable, when we plug in 0 and when we plug in 1 for x in this linear model equation. So that's all fine if we have a categorical variable with just 2 levels, but what happens if we want to break down our categorical variable into more than 2 levels? For example, if we're still interested in region, what if I don't want to just split my countries or my states into west versus east, but what if I want to have an indicator for states in the Midwest, states in the West, states in the South, and states in the Northeast? So I have 4 different categories. Well, I can't just put one region variable in my model. I still need to just use dummy variables, but I'm going to transform my categorical variable into a series of dummy variables. So what that means is that I'm going to create a Midwest variable that is equal to 1 anytime a state is in the Midwest, and 0 otherwise. And then I'm going to create a West variable that's equal to 1 anytime the state is in the West, and 0 otherwise. I'm going to create a South variable that's equal to 1 anytime a state is in the South, and 0 otherwise. So that's how I go from a categorical variable with many levels and transform it into a series of dummy variables. So when I do this, I'm going to put all but one of those variables into my model. So I still need a reference category. Remember, when we had just 2 levels, just west and east, we put west into the model and left east out. When I have multiple levels in my categorical variable, I'm going to put 3 of those 4 in the model and leave the 4th out as my reference category. But I'm still going to be able to learn something about the states in that reference category, which I'll talk about in just a second. So first, I've put all of these dummy variables into this model. Which of my region indicators have I left out? Which one is the reference level? So in this case, I have indicators for Midwest, West, and South in my model, and I've left out Northeast as the reference group. So the Northeast indicator variable, a variable that's equal to 1 when the state is in the Northeast and 0 otherwise, I don't include in my model. I can't put all 4 categorical variables in this model. I have to leave one of the categories out, otherwise my model will not estimate. So based on this output here, all of these different estimates for the different slope coefficients for each of these variables in the model, see if you can tell which of the regions, Midwest, West, South, or the reference category, Northeast, in which region do we have the lowest poverty percentage. Pause the video and see if you can puzzle that one out. So the answer is that states in the Northeast have the lowest predicted poverty percentage. So we can go through this by solving out this linear regression equation to find our predicted values for different values of the independent variables in the model. So we have different slope coefficients for each of the independent variables that we included. So we have the beta for Midwest is equal to 0.03, the beta for West is equal to 1.79, the beta for South is equal to 4.16. So for a 1 unit increase in Midwest, the associated increase in the poverty percentage is 0.03, and so on. So if we go ahead and solve this out, let's look, for example, at at the regression equation for West. So if we solve for our predicted value of y, our predicted value of the poverty percentage, we're going to have our intercept, 9.50, plus the beta for Midwest times the value for Midwest. So remember, if this is a western state, then it's not in the Midwest. So the Midwest x gets 0. So we take 0.03 times 0 is just 0. And then we take the beta for West, which is equal to 1.79, times the x value for the West variable. So if the state is in the West, the indicator variable will be equal to 1. So you have 1.79 times 1. And then plus the beta for South, which is 4.16, times the x value for South. So our state is in the West, not in the South. So that variable is equal to 0. So we have 4.16 times 0. So altogether, that's 9.5 plus 0 plus 1.79 plus 0 gives us an estimated y of 11.29%. And we can do that for all of the variables. Now remember, for Northeast, for our reference category, we have our intercept, 9.5, plus a 0 for Midwest, because the state's not in the Midwest, plus a 0 for West, because the state's not in the West, plus a 0 for South. So that's going to give us, for Northeast, an estimated poverty percentage of 9.5%. So because Midwest, West, and South, each of those categories all have positive slope coefficients, that means that for states in any of those categories, they're going to have something added to the estimate. If any of them had negative slope coefficients, they'd have something subtracted from the estimate, which would mean that they are getting a lower predicted value of y. But in this particular example, all of those have positive slope coefficients, and so it turns out that northeastern states are the ones that have the lowest predicted poverty percentage when we estimate this model. So that is sort of a quick and dirty explanation of how we use categorical variables in a linear regression model like this. And that brings us to the end of this lecture on least squares regression. Thank you for hanging with me. We're going to be talking about regression a lot more in the next lecture and in the next couple of weeks. So you want to make sure that you have these basics down before you move on. So I will see you next time.